So here is an announcement. People who have registered for the conference but not yet signed on the registration form, you can please go to the reception counter in the main building and do the and register yourself. Okay.
We are happy to have Suvrat from ICTS. He will be talking about quantum gravity, locality, and the reversibility of time.
Can you hear me? It's on? Yeah. Okay. Okay. Can you hear me now? Okay. Okay. So thank you, Roji, and thank you very much to the organizers for inviting me to this wonderful meeting. I'm really glad to be back at IMSC. Always have a very nice time when I come here. So I'm going to talk to you about a bunch of different things. Sandeep already gave you an overview of string theory, a very nice overview of string theory in the morning. I'm going to talk about something much narrower. So the scope of my talk is not that broad, but I'm going to speak about a rather narrow topic which has to do with how quantum information is localized in theories of quantum gravity. But maybe one thing I should say which will relate it to the previous lectures is that this is not something that the kind of physics I'm going to talk about is not something that requires is going to, as you'll see, is not something that requires details of string theory, but it's inspired, or the results, final results, were first seen in string theory, as Sandeep explained in the morning. So this has to do with holography and the holographic properties of gravity. And in principle, the kinds of arguments I'm giving now are arguments that one could have given 30 years ago. But people didn't give, and in fact people who work on other aspects of gravity still sometimes find surprising because it required in some sense the existence of these exact models within string theory to explain these properties of gravity. So since this session is in some sense geared towards understanding the relevance of quantum mechanics, or how string theory fits into our advances in quantum mechanics, I should explain that the way the perspective here is this, that it often happens string theory might point you towards interesting results and interesting directions, and later you might find that there is a way to argue for those results that's independent of the details of string theory, but string theory was important for you to have thought of those directions in the first place. So before I go on and talk about details of these phenomena that I'm about to describe, that I think are very interesting, although they are just a small part of the big story, I should this work that's been done in collaboration with many collaborators over the past 5 or 6 years. Most recently, my current student Ashik and former student Tunir, who's now a postdoc at TIFR. Also some work we did with postdoc Victor and former students Priyadarshi and Joydeep. And Alok is not in the audience, but a lot of this goes back to some work that we did now about 5 years ago with Alok and Siddharth and Pushkal and Chandramouli. Siddharth, Pushkal and Chandramouli were at ICTS, and Olga, who was a postdoc at that time at Perimeter, now in a faculty position in France. Also a number of papers that we wrote with a large group of collaborators, Hao, Andreas, Carlos, Lisa, Marcus and Sanjeet. And even though on these recent papers Kyriakos Papadimos has not been there, a lot of these ideas in some sense are much older, and they go back to much older work that we did with Kyriakos. So what I want to say is there are several references here, but I'm going to summarize work that's been done in collaboration with many people. Okay. So let me try and tell you the central message of this talk, which I'm going to try and persuade you of. So the central message of this talk, as I said, is about how quantum mechanics and putting together quantum mechanics and gravity changes some rather simple ways in which we think of how quantum information is localized. So before I tell you, how things work in the presence of gravity, I want to remind you of something very simple about quantum field theories, not even quantum field theories, about quantum mechanical systems that is so obvious that we often take it for granted. Okay? So this is a picture of some set of qubits. Okay, it's just some set of qubits, and I've divided them just by hand into some qubits in pink and some qubits in yellow. What's the problem? Oh, I see. Okay. So it tends to fall off, I'm thinking, but okay. Okay, so here's a set of qubits, and I've divided them by hand. This is just at one instant of time. Okay, it's just a set of qubits. It's a snapshot of a set of qubits at one instant of time, and I've divided them into a set of pink qubits and a set of yellow qubits just by hand. I chose to call the qubits inside some region pink and outside some region yellow. And the only geometric part of this configuration that you should keep in mind, which will be important later, is that the yellow qubits surround the pink qubits. Okay? Now there's something so trivial that it's hardly worth saying, which is that in general in a quantum mechanical system you can specify the state of the pink qubits independently of the state of the yellow qubits. Yeah? So for instance, if you go from this picture to this picture, I change this qubit from being up to down, I change this qubit from being maybe this one also from being up to down, maybe this one from being down to being up here, and I did some other changes on the other side, and those are just changes which you can do in a completely uncorrelated way. Okay? So we are not trying here to get the ground state of the theory or do anything like that. We are just trying to ask what is the set of possible states in the theory, and it's an obvious fact that you can do, you can change the state inside and outside a bounded region independently in the way we usually think of quantum mechanical systems. Okay, so this idea, which is so trivial that it's something that we take for granted and often don't even state explicitly, which is why unless you've heard this talk before or heard me talk about this before, you might not even have seen slides of this kind because it's so trivial. This idea is actually very key to our notion that information is available inside some bounded region and it's not available outside that bounded region. So in ordinary quantum mechanical systems, I now have a continuum system. You can prepare a state. So this is all at one instant of time. Okay, all these cartoons are at one instant of time. You can think of a state where you have an observer who stays outside some bounded region, and what this cartoon is meant to indicate is that for this observer, everything in the world outside this region looks like it's in the vacuum. However, there is some excitation that lives inside the bounded region. So if you have an observer in this part of the space, then they think that there's some excitation in the space. So you have a localized excitation which exists in some bounded region, and outside everything looks like the vacuum. And not only can you prepare a state like this, you can also prepare a state where you change the form of the excitation in this bounded region, but you keep the outside region continuing to look like the vacuum. Okay? Now this is an important notion because it's key to our notion that information about some information is localized in some bounded region, right? There's some information in this region that corresponds to the fact that there's an excitation present there, and there are some details of the state that are confined to that local region, and the observer outside doesn't have access to those details. Now if the observer outside waits for some time, if they wait for the light crossing time of this region, then eventually light rays from inside will emerge outside, but here we are just talking about the preparation of initial states. Okay, this is, I hope, very simple. I'm belaboring a very simple point, so please don't let that confuse you. I should say though, I'm happy to take questions as we go along. So if there's anything in what I say that's confusing or that you'd like to ask about, please feel free to ask, and I'm happy to discuss as we go along. Okay, so this is the picture that's true in ordinary non-gravitational systems. Now what I want to tell you is that in a theory of gravity, the cartoon is that this is not true. So first of all, if you think even of a classical theory of gravity, then you will realize that it isn't possible, even in a classical theory of gravity, to prepare a state where you have some excitation or some energy in some bounded region, but everything outside looks like the vacuum. The reason it isn't possible is because we can go outside and we can make a measurement, and we can measure the total energy of the region just using the Gauss law, using gravitational forces. So even in the classical theory of gravity, if you put some excitation in some region, then it's true that as you go outside, even all the way to infinity, you can detect the fact that this part of the space is not in the vacuum. Okay. Yeah?
This can also be done for electromagnetism.
This actually cannot be done for electromagnetism because you can put positive and negative charges so that things outside look exactly the same. So you can create excitations in electromagnetism so that the net charge is zero. So if you go outside, everything looks.
You can also create
You can, with only positive charge you can, yes, but you can also create excitations.
That will be another.
That what?
That will be another.
If you have only positive charges, yes, but in electromagnetism you don't have only positive charges. So that will be important later, that one difference between gravity and electromagnetism, of course, is that in electromagnetism you have both positive and negative charges, but in gravity you don't. In gravity you have only positive charges. Okay, so as you're saying, even in classical gravity this is true. What I'm about to say though is more interesting. It has to do with this picture on the left, on the right, which is that I'm about to explain. This will be one of the central points. It's a simple physical point which I'd like all of you to get at the end of this talk, is that in a theory of quantum gravity, and quantum mechanics here is important. So far in what I said, this was also true classically, right? You put some energy inside some region, you can measure it outside. I want to say now in the theory of quantum gravity, if you reorient the energy, if you change the excitation inside, then this change is also available to an observer outside. An observer outside can make some measurements that can detect the fact that you made a change inside this bounded region. Now notice at this point this is a statement that's obviously false in classical gravity. Okay. In classical gravity there is famous Birkhoff's theorem that in fact also exists in a version also is available in Newtonian gravity, which tells you that if you take a spherically symmetric distribution of matter, all you're sensitive to is the total energy. Right? Therefore, if I redistribute the total energy in some way, I change the density while keeping the total energy constant. In classical gravity, I cannot detect what I have done unless I go and directly probe the region. However, the claim is going to be, and this is the main message that I'd like you to take away, is that in the theory of quantum gravity this isn't possible. Even if you try and redistribute the energy while keeping the total energy constant, the observer outside can with sufficiently accurate measurements determine what's happening inside. Okay? This is just a cartoon, but please keep this cartoon in mind. I'll try and make it precise as we go along, but this is going to be the cartoon picture of what I say, and I hope at the end of this talk at least this simple physical point is clear. Okay? Okay, so first I want to start with some really simple, since this is about 100 years of quantum mechanics, I want to start with some very simple physical argument for why would you believe that such a funny property is true of quantum gravity, right? Why would you even start to believe that something like this would be true? So I'm about to now give you some arguments. The arguments I'm giving you have the virtue that they are very simple physical arguments. They're not going to say anything very, very complicated. I'm not going to have too many equations. They of course have the disadvantage that because they're so simple, you will see that they're not a proof, and so then I'll try and give you more robust arguments. But for the next few slides I'm just going to try and give you some reason to believe that quantum gravity might have this property, that you cannot prepare two different states which differ inside a bounded region but coincide outside the bounded region. Okay? So why would you believe this is true? So let me start with quantum mechanics. What is the first thing we learned about quantum mechanics 100 years ago? One of the first things we learned about quantum mechanics 100 years ago was the uncertainty principle. And the uncertainty principle told us that if you think of a state in the theory and the state has a definite energy. In fact, uncertainty principle often phrased in terms of momentum and position, but momentum in a relativistic theory goes together with energy. So if you think of a state that has a definite energy, very sharply peaked energy, then such a state, its wave function is delocalized in position space. Okay? So the wave function of the state is delocalized in position space. This is something that we know and we are very familiar with using the uncertainty principle. However, the fact that there is this uncertainty principle doesn't prevent us in ordinary quantum mechanics from speaking of objects that are localized, right? This chalk is localized here, and then I throw it up and I catch it and it was localized in different places, but we don't believe the wave function of the chalk necessarily has to have a tail out there. And the way we do this, which is something very elementary, we teach this all the time, is we take different energy eigenstates and we start superposing them. Okay? So you take one energy eigenstate with one value of the energy, you add another energy eigenstate with a different value of the energy but the right phase, a third different energy eigenstate, fourth one, and in fact you have to add an infinite number of them. You can check, you always need an infinite sum of energy eigenstates, but if you do this with the right set of phases, then you can produce a wave function so that all these different energy eigenstates, their wave function interferes destructively outside a bounded region. So outside a bounded region the wave function has no support, but interferes constructively inside a bounded region, so that you now have a state which has an excitation in a bounded region but doesn't have an excitation outside the bounded region. Okay? This is what we do in usual quantum mechanics in order to create localized excitations. Okay? If you wanted to create a localized operator which is another way of, maybe thinking about it. You wanted to create an operator that acts on the theory and creates an excitation in one region, that's how you would do it. Okay, you'd superpose operators of different energies with the right phases, so that eventually you got something that acted only in one region. Good. Now what's different about gravity? Well, so this is also something that we learned now maybe more than 100 years ago, 300 years ago, which is that gravity obeys the Gauss law. Okay? And it's in fact the same classical effect that we were talking about. It's the fact that if you put some energy inside some bounded region, then you can go out and take a big Gaussian sphere and you can integrate the gravitational flux on that Gaussian sphere, and by doing that integral you can determine what the energy inside is. In fact, the Gauss law is very fundamental, because in general relativity it's even more fundamental, because it is the only good definition of mass and energy that we have. In fact, in GR, if you want to define the mass and energy, you define it by saying you go out to infinity and you look at the behavior of the metric at infinity and you take some derivatives and you integrate it. This is called the ADM Hamiltonian. It doesn't matter, it's basically just integrating, the flux of the gravitational field on this Gaussian sphere. But in GR, that's a very fundamental concept, because that's what tells you how you define the energy in GR. Okay. So what's different about gravity is that there's a Gauss law. Now you might say, well, fine, how are these two related? You told me in quantum mechanics I had to superpose different wave functions. In gravity there's a Gauss law. If you think a little about what happens if you try to put together the uncertainty principle together with the Gauss law, you will see that in a quantum theory, if you want to think of a state of the theory that's an eigenstate of the energy, okay? So you want to think of a state of the theory that's an eigenstate of the total energy, then such a state might have some kind of excitation, it might have some kind of excitation in the bulk, but in addition to that there is another degree of freedom, and that degree of freedom is some flux of the gravitational field at infinity, which tells you that whatever energy you had in the bulk must equal this gravitational degree of freedom out at infinity. Okay, this is what's called a constraint, but it's something very physical. It's just using the Gauss law. It's telling you that in a theory of gravity, you put some stuff in the bulk, and you want an energy eigenstate, so you can have some excitation in the bulk, but in addition there is this additional degree of freedom which has to be set so that it measures the energy of this excitation. Okay? So there are various words that go along with it. Sometimes we say in the quantum theory of gravity, every excitation must be dressed with a gravitational tail which measures the energy of the excitation. Now if you go back to the picture that I described at the beginning, where you were trying to create these localized excitations by creating interference between different energy eigenstates, you now see that you're in trouble, because you wrote down this energy eigenstate. So maybe you had a theory of matter coupled to gravity, you wrote down some energy eigenstate which had some energy, but now that energy eigenstate can't live in splendid isolation, it comes together with the gravitational tail that lives outside, and then you add to it another energy eigenstate, but that energy eigenstate that you wanted to interfere destructively with the first one now comes with its separate gravitational tail, which is different from the gravitational tail of the original energy eigenstate. And because it was important to get localized excitations, that you had to superpose all of these different energy eigenstates, you now find that process of superposition causing destructive interference is obstructed by the existence of these gravitational tails. Okay? So the intuition, the physical intuition that you should keep in mind is that the existence of these gravitational tails prevents constructive interference inside a bounded region and destructive interference outside the bounded region. Okay? So that is the reason why in a theory of gravity you cannot have a setup where you do something inside some bounded region, you create some excitation, or you reorient some energy locally while keeping everything outside. Okay? What I gave you right now is of course not a proof, but it's an indicative argument. I'll give you some more robust arguments, and it's some argument that you should keep in mind for physical intuition for why what I said is true. Yes?
Subrat, so the gravitational parts are orthogonal.
The gravitational parts in this setup are orthogonal, yes.
That's why they will be destructive.
Yes. That's why you will not be able to make them interfere. That's right.
It's like tracing those parts.
So tracing those parts is a little more complicated, but I'll describe how you go back to a non-gravitational limit a little later. But yeah, the presence of those parts tells you if you just add up these wave functions, you won't manage to get constructive interference inside some region and destructive interference outside. Yeah.
So even in classical gravity, you said that the tail should have an analog, right? Because you should be able to apply Gauss's.
So that you see that good. That's a good question. You see the issue is in classical gravity there is no notion of an energy eigenstate that you have to superpose. Right? So there are two pieces of physics that are going here. This is after all a conference on 100 years of quantum mechanics. Right? The two pieces of physics that are going in here is not only that everything has to be entangled with the tail, but also that in order to get an excitation that's confined to this room and that doesn't exist outside, I have to superpose many different energy eigenstates in a delicate way so as to get destructive interference outside the room and constructive interference inside. In classical gravity there is no such thing. I just say I have some mass of energy and and I dress it with the right gravitational tail. So there is no notion of saying, oh, I have to take different energy eigenstates and can I superpose them in order to get destructive interference or not. Okay? So that's what's important about the quantum
So you're
mechanical
pointing out that in quantum theory at least there was the possibility, or maybe there is the possibility of cancellation, but it should not work.
No.
But in classical there is no such.
In the classical theory, you don't even have to worry about cancellation because you're never trying to arrange for destructive interference. You just say here is a localized excitation and this excitation is localized. In the quantum theory, you might have worried, even in the absence of gravity, oh, can I get localized excitations? And the answer is yes, you can. And how you get them is you add together different energy eigenstates and you arrange for them to interfere destructively outside but constructively inside. But now I'm saying in the theory of gravity, that process is in trouble and therefore you cannot have strictly localized excitations. In the classical theory, the whole question doesn't arise. Okay, good. So now I said something very, very cartoonish. So I've been giving you cartoons now for 20 minutes. So now I'm going to go and say a few more precise things. So now I want to give you a sense of what the precise results are. I'm not going to go into details of what the precise results are, but I want to now make some precise statements since I've been making a lot of cartoonish statements. But please hang tight. I'll go back to saying things which are simpler. Some of this might seem formal, but I hope I'll at least give you a sense of what the precise results are that try and make this picture, accurate, the picture that I just presented. So the first thing I want to say is that, and now when I talk about these precise pictures, one thing that's maybe before I go here, the way we need to work in quantum gravity always is that in quantum gravity we imagine that we have some space-time, and Sandeep was talking about the cosmological constant in the morning, but we fix the asymptotics of the space-time. Okay? So you can fix the asymptotics to being asymptotically flat space where there is no cosmological constant, or you can fix the asymptotics to being asymptotically anti-de Sitter space, which string theorists are very fond of but might not have much to do with the world. Or you can talk about asymptotically de Sitter space, which is the case with the positive cosmological constant. Okay? But whatever you do in quantum gravity, we generally believe that it's useful to allow the metric to fluctuate and allow quantum gravity effects to do whatever they like. But when you go very far away, there is a sense in which the asymptotic geometry of space-time is fixed. Okay? So the results are, when we try and make this picture that I just presented precise, it's not really possible beyond perturbation theory. In perturbation theory, some of the cartoons that I presented can actually be made precise, but if one wants to go beyond perturbation theory, then it's very hard to make the cartoons that I presented precise, because all these cartoons are about bulk pictures and bulk excitations and so on, and those are things that are very hard to define in a theory of quantum gravity, and therefore the precise results that we have are always about asymptotic operator algebras. They're always about some property at infinity. Okay? So what I'm now about to show you is how at infinity there is a signature of the properties that I just described, and how at infinity the structure of asymptotic algebras in a theory of gravity and with or without gravity is different. And after this I'll then go back and talk about some perturbative signatures of what I said. Okay, so let me first talk about asymptotically flat space. So asymptotically flat space is a case where you have no cosmological constant. This picture here is a picture that some of you are familiar with, but some of you might not be familiar with. It's my depiction of what's called a conformal compactification of flat space. This is a case where flat space, asymptotically flat space goes out to infinity, right? But that's hard to draw. So it's often convenient to rescale space and time so that you have this picture where this part is what's called the future null boundary of asymptotically flat space. It's called Scri plus. This part is the future past null boundary of asymptotically flat space, which is roughly saying that you look at all light rays and you look at where they end up in the future and where they came from in the future. Okay? So these are light rays that of course travel in space as well as in time, in the past and in the future. And if you look at the collection of that gives you this region called Scri minus, and this region is called Scri plus. Okay. So this is the way we want to, this is the convenient way to speak of the asymptotics of asymptotically flat space. Okay. So in a non-gravitational theory, if you think of asymptotically flat space, and just one more thing, I said, you look at the set of light rays and you look at where they end up in the far future, the far past, but the property of a light ray is that it keeps t minus r fixed. Okay. So if you have a light ray which is expanding outwards radially, then this light ray is, as time goes, it's forward, it becomes larger and larger in radius. However, t minus r is kept fixed, and this coordinate u is t minus r. So you can classify different light rays by just looking at the value of t minus r for them. Okay. So this future null infinity is characterized by different values of this coordinate u, which you can think of as t minus r. So, these coordinates u have the property that in a non-gravitational theory, you can think of different observables at different values of u. So you can think of a set of observables, all of which are distinct, which live at different values of u. The claim is that in a theory of gravity, any observable in this region can be approximated arbitrarily well by an observable from this red band, from this thin red band. Okay. This thin red band, even though it's, it looks very thin on the diagram, is actually what's called a semi-infinite interval on Scri+. But the claim is that any operator in this algebra, or I shouldn't use those words, any observable on Scri+ can be approximated arbitrarily well by an observable near the past boundary of Scri+. And if you want to think back to the cartoon that I showed you, one other way of thinking of Scri+ is to think of a spatial slice, but to think of a spatial slice that's tilted up in such a way that it asymptotes to this. Okay. So those of you who've seen special relativity, the way you draw light rays is you draw light rays as 45-degree lines. So you're taking a spatial slice and you're kind of tilting it up, and you see this is like the boundary of the spatial slice. And what is being said here is that if you want to make an observation somewhere in the bulk which is in this region, such an observation can always be replicated by an observation near the boundary of the region. Okay. Which is why you cannot have distinct states which look different for observations in the bulk but look the same for observations outside that. Okay, let me give you also the precise result in asymptotically anti-de Sitter space. Anti-de Sitter space has a slightly different structure of infinity from the structure that we have in asymptotically flat space. It's, as I said, the case where string theorists like to think about a lot. And in asymptotically anti-de Sitter space, one way to think about it is, in fact, one reason why string theorists like it a lot is because it's a good model of how to think of quantum gravity in a box. Okay? So this is one way you can think of asymptotically anti-de Sitter space. It's a space where you have gravity and it's confined to a box, and on the y-axis you have time going up. Okay? And stuff which is deep in the bulk, which is somewhere here. So if you think it could be somewhere here behind this, you should think of this as a solid cylinder. Eventually signals from there reach the boundary at late times. Okay? Therefore, if you think of an observer who just sits on the boundary and is making measurements on the boundary, then this observer making measurements at different times knows about what's happening at different regions in the bulk. Okay? So it's just like a cylinder, you're making observations on the cylinder. As you go further into the future, you can see deeper into the bulk. Okay? So in a non-gravitational theory, if you want to think of the set of all distinct observables in the theory, the set of all distinct observables in the theory is given by just looking at the set of all operators on the boundary at different values of time. Okay? However, in a theory of gravity, any observable in this set can be approximated arbitrarily well from an observable in a small time band on the boundary. So if you wanted to go back to this picture that I just gave you, you might have thought that someone who has detectors that are only active in the small time band can't actually see deep into the bulk, right? Because they don't have time for light rays from the bulk to reach them. However, the claim is that in the theory of gravity, you look at observables in a small time band, and that's sufficient to reconstruct the entire boundary. Now, those of you who are familiar with the famous ADS-CFT correspondence will know that this is almost obvious result from the point of view of string theory, because we know that in the theory of gravity, it is true that the entire boundary theory lives on a single time slice, and we know that in the cases where the ADS-CFT correspondence is believed to hold, that the entire bulk can be reduced to a theory that lives only on the boundary. However, the arguments I'll try and describe are not arguments that, as I said at the beginning, rely on the details of string theoretic compactive or string theory, but just rely on rather general properties of gravity as I described in the beginning. Okay, let me also say something about what happens in asymptotically de Sitter space. This picture has slightly different flavor from the previous two, but then I'll try and unify all three of them. This is the structure of asymptotically de Sitter space. De Sitter space is a space which expands exponentially in the future and also in the past. Okay? So the fact that you have this positive cosmological constant causes the space to blow up exponentially in the future, and if you ask what happened in the past, well, it came from something like that in the past. Now, if you're some observer in de Sitter space in a non-gravitational theory, you might have thought that you could make different observations at different points very far in the future. However, the claim is that in the theory of gravity, if you made observations on the small region, this set of observations is complete. This claim actually needs to be, it needs to be made much more precise. I'm not going to go into subtleties about how exactly you define observables in this region. And so to some extent, the result I'm stating here is a true result, but I haven't defined for you exactly how to define observables in the region, so please take it with a slight note of caution. Okay? So what I told you so far is that there are three different asymptotics you could consider, which is the asymptotics of asymptotically flat space, the asymptotics of anti-de Sitter space, and the asymptotics of de Sitter space. And in all three cases, I told you that the set of observables that you would have in a non-gravitational theory is somehow restricted in a theory of gravity. Okay? And as I said, the picture I always want you to keep in mind is the picture I presented at the beginning, which says that in the theory of gravity, the set of observables, outside a bounded region always know what's happening inside the bounded region. In fact, that's the way you should think about how to unify the picture in anti-de Sitter space and de Sitter space. Sometimes in the string theory parlance, this effect that we call holography is expressed by saying that information about the bulk lives at the boundary. However, there is a slightly nicer way to say it that unifies what happens in flat space, in ADS and de Sitter space, which is that the complement of a bounded region also has all information about the state. So also in particular has information about what's happening in the region. Okay? You see, in ADS and flat space is kind of obvious, because if you think of the complement of a bounded region, this region always goes off to infinity. So if I say that the holographic principle is that all information is available in infinity, I could just as well say all information is available in the complement of a bounded region. However, in de Sitter space, it's a little more interesting, because in de Sitter space, the spatial slices that you have are closed. Okay? In this picture, you might have thought that the purple region is a complement of the bounded region, which is blue, but it's also true that the blue region is a complement of a bounded region, which is purple. Okay? Therefore, in de Sitter space, you are led to a rather interesting picture, which is that in fact you make observations on any small open set, and that set of observations is complete and tells you about what's happening everywhere. Okay? So that's one way in which you can think of this picture of how information is localized in gravity in a unified way, and the slogan would be that it's always sufficient to make observations in the complement of a bounded region to know everything about the state. Okay, so far I've said various things. What I've done is I gave you some cartoons, and then I told you what some, I sketched for you what some pictures about asymptotic operator algebras were. I'm now going to give you a sketch of how we prove these results. Once again, this might be something that might not immediately be familiar, but I just want to explain what are the physical assumptions that need to go in to prove these results, which will also go into this question of the positivity of energy. But are there any questions at this point? Yeah.
So this picture you had with the cylinder and a slice, time slice.
Yes.
So the information in the bulk is contained in all of the boundary, right? So how is it that you can only look at a small time slice?
Yeah, good. You see, so the holographic principle actually tells you that the theory in the bulk can be recast in terms of the theory on a boundary. That's how ADS CFT works. Let me just. However, if you have a theory on the boundary, all details of the state are given by an instant of time. If I tell you the state of the theory at one instant of time, that's all the information there is about the state. I don't have to tell you how things evolve, because the theory has an autonomous Hamiltonian, and therefore things evolve according to the Hamiltonian. So what is special about holography is not that if you give me all boundary values, I can reconstruct the bulk. That is not special, even though sometimes people think of that as holography. That is just solving a boundary value problem. That we do all the time. That happens with or without gravity. So if I tell you all the boundary data, can you reconstruct the bulk? Yes, but so big deal. What is special about gravity is I don't tell you all the boundary data. I only tell you boundary data on an instant of time. Here actually we need a time band. but I only tell you boundary data on a small band of time, and that's enough to tell me everything that's happening in the bulk. So it looks like the boundary value problem is ill-defined or it's ill-posed. Nevertheless, you have to do something more clever to reconstruct data from the boundary.
That should be true in a non-gravitational.
No, in a non-gravitational theory, it's not true. So the left-hand side is what's true in a non-gravitational theory. You see, in a non-gravitational theory, it's just a question of solving a boundary value problem, which is, you give me, let's say you tell me what's happening at this, let's say I have a detector here. I surround the walls of the room with a detector. And I tell you what's happening at all times in the walls of the room. The walls of the room will always know what's happening everywhere in the bulk, because eventually signals from the bulk will reach the walls of the room. So in a non-gravitational theory also, if I tell you what's happening in the boundary, but for all times, that's enough to determine what's happening in the bulk for all times, right? Because signals from the bulk reach the boundary. In a holographic theory, I can have detectors that only make a measurement for an instantaneous amount of time, but they already know what's happening in the bulk. That's very surprising, because it looks like they're reaching into the bulk and determining what's happening, even though they were only on for a very small amount of time. Yes?
Sort of very elementary comment.
Yes.
You made a statement that Gauss told us that, I mean, you don't know anything about the inside. You can only measure things outside, and that's because of the Gauss theory. Now, consider a distribution which is non-homogeneous,
Yes.
but also not spherically symmetrical.
Yes, yes.
That will lead to obviously
It doesn't have
a
this.
situation where it is
Yeah.
you can make out.
It doesn't
And if
have-
that fluctuates.
No.
It will
So-
have its effect.
No. So, it's true that by using, the reason I gave the example of spherically symmetric distributions was, I just wanted one counter example. Now, it's true that you could have more multipole moments. But in general, even if I give you a large number of multipole moments, it's still not sufficient to determine everything that's happening in the bulk. For instance, I could have replaced, let's say I had two fields of matter. I had, let's say you're only measuring gravitational fields. You're talking now of the classical theory, right? Let's say I replaced all my electrons with positrons and vice versa, right? I've changed the details of what's happening in the matter. But, maybe the total charge is 0. I've changed the details of what's happening with the matter, but the mass distribution is exactly the same. The state is different. So you see, it's an example of how you can have many distinct initial states that have the same gravitational field outside in the classical theory. The surprising thing is that in the quantum theory you cannot. You can't change your electrons with positrons and keep everything outside the same. Yes.
Yeah, this picture of cylinder that you have, but the cylinder is time-like, right?
The cylinder is time-like. Oh,
And
thank you.
therefore you cannot put arbitrary boundary values on the entire cylinder. It has to be consistent with the slice you choose.
Yeah, good. So first point, I guess, which I should have emphasized sufficiently is, whenever I draw these diagrams, in the y-axis I almost always have time. Okay? Unless I state otherwise, the y-axis always is time. It's not a spatial cylinder. The second thing is that, in the bulk, you could in fact have many different initial conditions. What you're thinking about is that there's a light crossing time in the bulk, and what you want to say is that maybe if you're an empty ADS, or if you're working about empty ADS, then you can independently specify data for a length of time pi, or for a time band of length pi. Let's say pi is the light crossing time. Okay? So you're thinking that you can independently, however, you can have more exotic things happening in the bulk. For instance, there could be a black hole in the bulk. If there was a black hole in the bulk, then in fact you could have specified data for all these times. Okay? This is a question of, what are the kinds of Fourier modes you get when you expand things in time. And indeed it's true in empty areas, those Fourier modes are integrally quantized, and therefore once you specify something for a length of time, for a time of length pi, or time of duration pi, then you have specified everything for all times. But in the presence of black holes, that's not true. So in general, the data in a non-gravitational theory can extend beyond pi and can be everything. But in a gravitational theory, you don't need to specify things even for pi. You just need to specify them for an epsilon interval.
Yeah, I have to understand it, but
Was my answer not clear? Or?
no, I don't see the distinction between gravitational and non-gravitational case, because as far as initial value is concerned, on the boundary,
Yes.
if that is a slice,
Yes.
when you say that from bulk some information comes,
Yes.
which means the system is not closed.
No, the system is closed.
As far as the boundary is concerned,
The
it's not
system is
closed.
closed.
No, not the whole system. Only the boundary, if I look, boundary is time-like.
The boundary is of course not a closed system in
No,
non-gravitational theory.
exactly.
Yes. But in a gravitational theory it is.
Why is that?
Well, that's the argument, but that's the claim.
Oh, okay.
In a gravitational theory it is.
But I
That's the
don't-
claim of, the
okay.
claim of holography is that it is. Yeah, exactly. In a non-gravitational theory you could have stuff from the bulk which would come and hit Q. And so the boundary is not a closed system. That's why you need to specify data for intervals. Maybe I misunderstood your question. In a theory of gravity, the boundary is closed. The simple one-line answer which I can give you later is the Hamiltonian is a part of the boundary algebra. So you give me operators in the boundary, you can evolve them forward and backward with the Hamiltonian. There's nothing more I need to know. But I'll give you a slightly better argument. Yeah. Okay. Actually, we don't know how to make epsilon 0. It is a very subtle question of whether you can have a time slice, or you need a slight interval of time. Ronak was explaining to me that even in quantum field theory, if you really want to define it, you shouldn't speak of a time slice, but of a slight band. This is actually a subtle question. Certainly in the arguments we have, we can't make epsilon 0. Because the arguments rely on some analyticity properties for which we need some finite epsilon. Okay, let me now, I want to give you a sense of what are the physical assumptions that go in. So I want to give you a sense of the sketch of the proof. Actually, please don't feel obliged to follow all the details, but what I want to explain is what are the assumptions that go into proving a strong result of this kind. So I'll tell you how we prove this result in asymptotically flat space. Okay. So, the kinds of assumptions we need to make, of course, you can't get something out which is a strong result about theories of quantum gravity which you want to claim hold for all kinds of theories of quantum gravity without putting some assumptions in about the theory. And the assumptions we'll make, the first one which I already explained at some length, is that the asymptotic algebra, by which I mean if you go very far away in your space-time, then the language of quantum field theory is still a good language to use to describe things. Okay? That's the statement, that's one of the assumptions we need to use. That's kind of a statement of how you formulate the theory. Okay? The second is that we need to assume some version of the Gauss law, which remember I said was very important in the physical cartoon I showed you at the beginning. And in fact what we need to assume is that there are some charges in the quantum theory that you can measure that are sufficient to at least identify the vacuum of the theory. And finally we'll need to assume that the Hamiltonian is bounded below, which is in fact related to a question that you asked, which is that it's important, of course, that in a theory of gravity you have only positive charges, only positive energy and not negative energy. And I'm going to try and sketch for you very quickly how if you put together these assumptions which we can't prove, you could come up with this conclusion that in a theory of gravity, if you make observables, you make observations only on one time slice near the past boundary of Scri plus, or a small interval near the past boundary of Scri plus, that's sufficient to determine all observables in the theory. Okay, so as I said, we assume that this language of quantum field theory makes sense. So there's some set of all observables in the theory. In a non-gravitational theory, this is the same cone picture that I showed you. You have observables labeled by different values of when the light ray goes and hits the boundary. And so if you think of the set of all observables, they are just a set of all operators in the theory at different values of this u, which is t minus r, as I said, and you multiply them together. I want to say, however, in a theory of gravity, this set of operators can in fact be obtained from a set of operators that naively look smaller, which is the same structure, but where I've restricted these values to being minus infinity to being minus 1 over epsilon. Okay, so this red region. So I want to say that all operators in this future boundary can be obtained from operators in this red region. Okay, so the first thing we need, as I said, is that the Hamiltonian is bounded below. The way it goes into this argument, in fact, is that it tells you that if you think of the set of all states in the theory, that you get by starting with the vacuum and exciting it in all possible ways with these boundary operators, then all these states you can in fact get also by exciting the vacuum with a set of operators in this small region. In fact, for this particular result, we don't even need gravity. This particular result is a manifestation of the fact that the vacuum of the theory has a lot of entanglement. Okay? So the first result is that any state in the theory which naively you would have thought you would need to act with all operators in the theory on the vacuum to get, you can in fact get by acting with a subset of operators in the vacuum. I'm not explaining at this point how we prove this result. I'm just telling you that it's a true result because I want to explain to you what are the assumptions and what the structure of this proof is. Okay? The second thing I said, remember, is that the vacua can be identified at infinity. In particular, if you want to think of the Gauss law, you can measure the energy at infinity. But what quantum mechanics tells you is when you measure the energy, there's some probability of getting different values, and the Born rule in fact tells you that the probability of getting 0 is given by the expectation value of this projector onto the vacuum. This is something that's very unusual in gravity. In no other theory is it the case that you can determine from infinity whether you're in the vacuum or not. And therefore, an observer who just sits far away at infinity can, by measuring the energy, determine whether they're in the vacuum or not. So in particular, they have access to this observable, which is the projector on the vacuum. If you now think of any operator in the theory, you expand it out in a complete basis of states, which, as I said, is very basic to quantum mechanics. The first thing I told you is that any state here you can get by acting with an observable in the small set of observables, or seemingly small set of observables in the vacuum. And then I told you that the projector on the vacuum was also an element of the small set of observables. And so now you see that any operator in the theory you can write as a product of three elements of the small set of observables. And because the set of observables in quantum mechanics is always closed, this tells you that any observable in the theory you can represent in this way in terms of observables near the sparse boundary. Okay? So for those of you who are not familiar with these techniques, it might seem, this proof might seem that I went way too fast. And so I don't really want you to appreciate, I'm going to give you some different perspectives in this. I don't want you to follow all the steps of the proof. All I want you to follow is get a sense of is the structure of how the arguments work and what are the physical assumptions that go into the arguments. Okay, the algebra here is not very complicated, but it might still seem like a very surprising result that we got. So I'd invite you to go and think about this later. But for now, I just want you to think about what are the assumptions we needed and give you a sense of what are the kinds of arguments that are made. Okay. In fact, yes. 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 Yes.
Okay.
Yes. Actually,
Because it keeps saying a small set.
well, small I was just saying in terms of a set of observables localized on a small region of the infinite boundary. So seemingly smaller. The question of uncountably versus countably might be a philosophical distinction, but I feel we are always okay talking about countably infinite sets, but fine. Yeah. Okay, I'm now going to give you some different perspectives, right? So what I've done so far is I gave you some cartoon, and then I gave you some statements of results, and I gave you some sketch of how we prove those results. If some of the last 20 minutes seem to go a little fast, I'm now going to give you different ways of thinking about it. One of them is just about perturbation theory, okay, how you would see these results in perturbation theory. So, I've been telling you so far that if you think of asymptotically flat space, then in asymptotically flat space, or if you're on the boundaries of this room, then in the boundaries of the room you can do something in the theory of gravity and determine what's happening in the bulk. Okay? So this is a picture of now the boundaries of the room, because in GR we like to draw pictures in a strange way. We've drawn it in a strange way, but you can kind of forget about that. This is us, or this is some spider or fly on the walls of the room. Okay, and that they are allowed to make measurements in this little red region. Okay, the way you should think of it is you have some fly or some bug that lives on the walls of this room, and this bug has access to a detector, but only for a short amount of time. Okay, they can't make a measurement for all amounts of time. Okay. Then something happens in the bulk of the room. Okay, so maybe I say something, okay, and they have to determine what I said. Okay. That's this blue thing here. Okay, and the way I've set up this problem mathematically is you have the vacuum and you excite the vacuum with a unitary operator. The unitary operator is such that you have some field in the theory. You take the field and you smear it with some function, and then you put the whole thing inside an exponent and you act in the vacuum. Okay? The words I'm using to describe this, for those of you who are not familiar with this language of field theory, is just that it's an excitation. It's the kind of thing where you take the vacuum, so everything was still, and then you excite it, you say something. Okay? The fact that this function f has has some compact support is a statement that this function f, I said something for a short amount of time and then I stopped. Okay? So this is the statement, you make some excitation with this field O, but you modulate the excitation with some function f. This function f starts at some point and stops at some point. So this is the picture that you would get, which is you have something that goes off in the middle of the room, and then light rays go off and they go, they hit the boundary at a later time. Okay? And the challenge is, from what I've been saying, you want these observers to make a measurement at an earlier time before the light rays come and hit them to determine what is it that was said. The information that they need to recover is information about this function f. Okay? That is what was said. Okay, is it clear, or am I being, if I'm being very unclear, please stop, but if it's clear, I'll go along. Is at least the statement of the problem clear? Okay. The precise statement of the problem is you have to make some observations here in the state f, and you have to determine what this profile function f is. Okay. Without waiting for the light ray to go and hit the boundary. Okay. So that's the problem statement.
This is in a theory where holography is true.
No, this is in any theory of quantum gravity. Okay, so the argument is, by the way, that holography is true in any theory of quantum gravity.
Okay.
So
if
it's,
holography is not there, this will contradict the Green's function.
well,
Retarded Green's function.
if holography is, so in a theory of gravity, holography has to be there.
Okay, so we'll say that holography is there, is that?
Well, we won't say that. I'm just going to show you a calculation that will show you how these observers can determine what's happening. You are right that in a non-gravitational theory, the way this would propagate would be by means of some retarded effect. So you would have turned on some source, and there would be some retarded effect, and therefore that function would only have support in the future light cone, and therefore it would be impossible for someone here to determine what was happening there. Okay. However, what I'm trying to show you here is that if you, without even making many of the strong assumptions, if you just compute some simple observations, if you just compute some simple correlation functions, or just allow these people to make some simple observations, they can determine what this function f is. And so this picture of thinking in terms of the retarded Green's function is not correct when you think carefully about what happens in gravity. It is correct, of course, in some cases, but in some other cases it's not correct. Yes. Yes.
That a young man or woman should be able to, according to you, in a theory of gravity, be able to do an experiment today and tell us that in the future they will have grandkids and what their names are.
No, actually it's a good point, but that's not it's not an astrology thing for the following reason.
No, it's not astrology.
No, for the following
science
reason.
Says with gravity.
Science actually doesn't say that, because you see, you have information only about a bounded region. A young person today is also receiving information from outside. So it's very important here that these observations, but they have to surround infinity. They can't be on a localized region of infinity.
A young man who rigs up.
Yes, a young person who rigs up an experiment very far away can indeed determine this. Yes, so if you have a person, but of course that's very hard. So a simpler experiment, which in fact, as I said, one might be able to rig up, is you try and set up detectors on the boundary of the room to determine what's happening in the middle of the room in a time that's shorter than the light crossing time. Okay, so detectors are only on for an infinitesimal time, which is shorter than the time it takes to cross the walls of the room, and they have to determine what's happening in the room. Okay, that's what all astrologers are doing. No, Okay, maybe if the astrologers, who knows, we've had ancient wisdom, and maybe we knew about quantum gravity in the past, right? So this is maybe I can actually make a good, I might endear myself to the past, that be if I had to go to by explaining how in the past we knew about quantum gravity effects. More funding and many other things, yes. Okay, good. But let me explain. So this is how the astrologers do the computation. Okay, so the calculation they have to do is, you want to determine this function f, and what you do is you take this function f and you measure a 2-point function. A 2-point function is a function of the insertion of the energy, but not just of the energy. You have to measure a correlation function of the energy and also this other operator that creates the excitation that you had. If you measure this 2-point function, it's easy to see that you will get some answer, and the answer, even though this excitation was a localized excitation, this 2-point function has a non-zero value even when u is in this red band, and you will find that by using this 2-point function, you can in fact completely determine this function f. Okay? So the point is that it's not enough to only measure the energy, and this is why quantum mechanics is important. You have to measure correlated fluctuations of the energy at the boundary with other observables, and those correlated fluctuations are sufficient to tell you what's happening in the bulk. Okay? And this is a very simple example of how in this very simple state those correlated fluctuations are sufficient to determine what's happening in the bulk. Okay? The operator O was the operator that went into creating the state. Okay, so as you said, in fact you already asked this question about gauge theories and also about the Green's function. This whole thing would not make any sense in a theory without gravity. In a theory without gravity, for instance in electrodynamics, you have what are called localized unitary operators. So in the absence of gravity, you always have local gauge invariant operators. Well, let me not use those fancy words. You always have operators that are strictly localized, and those operators, are impossible to distinguish from the vacuum. So in the absence of gravity, there is nothing that these people can do, there's nothing the observer on the boundary can do that can determine what's happening in the bulk. And that's also related to this fact that if you make an excitation in the bulk, it propagates using the retarded Green's function, and these people on the boundary can't know what's happening in the bulk. Okay, this is also related to, maybe I'll skip over this part. This part was this shifting electrons to positrons and how you can detect that, but I'll skip over it. I'm happy to come back to that. Let me ask a different question since it's related to this issue of, the retarded Green's function. You could have asked, and maybe that's what you're thinking, how is it physically that these people who are sitting on the boundary learned about what was happening in the bulk without waiting for light rays to go there, right? You could have said, look, it seems like it violates causality. It looks almost like something jumped from here to there. In fact, the answer is that in the theory of gravity, one reason why it's a wrong thing to think in terms of the retarded Green's function is that what the retarded Green's function tells you is how the state responds if you turn on a localized source. If you insert some energy locally in some region and you want to ask how does the state respond, then the retarded Green's function is what tells you, using the commutator of what you turn on, the operator you turn on, the observable you're measuring, what you see. However, in a theory of gravity, it is not possible to turn on local sources. So even though I said that you have these observers who are sitting here and you have something that happens in the bulk, in fact that was a bit of a cheat, because this excitation that lives in the bulk, really you would have to trace back in a theory of gravity and would also have had to come from the boundary. So there is nothing that can happen autonomously in the bulk that didn't come from the boundary of the room. Okay, so that is what is special about gravity. In fact, if you take a step back and you think about it, you will see that even the classical Gauss law, forget about all these effects, even the classical Gauss law already has this feature. We know what the mass of the sun today is. We know it's 2 into 10 to the power 30 kg. How do we know it's 2 into 10 to the power 30 kg? The sun is not telegraphing us and telling us it's 2 into 10 to the power 30 kg. It is the fact that the mass that created the sun crossed where we are standing today. And when it crossed where we are standing today, it modified a component of the metric permanently, and it's that memory that we are today sensitive to. That's why even the classical Gauss law is not inconsistent with causality. The classical Gauss law is really a statement of memory. It's the fact that the mass that went in had to come from the Gaussian surface at some point, and that's why integrating the flux over the Gaussian surface lets you determine the mass at all times. And it's not possible for that mass to change without that mass from exiting the Gaussian surface. So even here these effects are not really in contradiction with causality, and the key thing you should realize is that in a theory of gravity you cannot locally change, insert or do anything. Okay? In a theory of gravity you have to send in energy from outside, and energy has to exit outside, and it's that reason that allows the boundary to know what's happening. In some sense it's like a generalized memory effect, although I use that word with some hesitation because memory is used for other things. Yeah. Okay, so yes.
So can one say that there is some trajectory on the boundary itself then, that that the observer is crossing?
So you see, it's the same thing that says that we know the mass of the sun, right? We are kind of living on the boundary. We can think of ourselves as living on the boundary of a Gaussian surface that's surrounding the sun. We are making a measurement today. The mass that made up the sun crossed us billions of years ago. But when the sun was formed, it modified the metric around it permanently, and that metric cannot be unmodified unless the sun itself explodes and that mass again crosses the Gaussian surface. So even though we are making a measurement today, what we are measuring is some memory of what formed the sun in the first place, and in some sense what's happening here is similar. However, in the classical theory, the only memory that remains is that of the total energy. But in the quantum theory, the statement is that the kind of memory that remains is much stronger, and by measuring all tails of, not just the energy but fluctuations of the energy and correlations of those energy fluctuations with other operators, you can determine everything that's inside. Well, so you see, the argument here is, the proof I gave you showed you that all operators in the bulk could be represented in terms of operators on the boundary. So that's a proof that no information can be transferred, because it tells you any observation you make all observations in the theory are complete if you just make observations on the boundary. Now I'm just trying to physically explain that result.
place spontaneously, that has nothing to do with information
No,
coming
you
in
see,
from the boundary.
you see the atom doesn't, the atom actually is in a wave function, and when we think of the atom decaying spontaneously, you're thinking of some decoherence process. In fact, what happens is there's a wave function of the atom, and the wave function of the atom continues to evolve in a way that's consistent with the Schrodinger equation. So, for instance, you could have a wave function of the atom and a wave function of a pointer, and maybe the pointer wave function and the atom wave function, entangle with each other. And so what will happen is you might get then two branches of the wave function, which are, atom is in 0 and pointer is in 0, plus atom is in 1 and pointer is in 1. But there is only one wave function. There isn't any indeterminacy in quantum mechanics. That's why we have a Heisenberg picture, right? Because there's only one description of the state. So you shouldn't think in terms of something happening in the bulk that's unpredictable. If I give you details of the state, then that completely determines the past and the future. What? No, vacuum fluctuations are just again a description of the state. Vacuum fluctuations are words that we use. In the end, the state is a certain wave function. That wave function, might look like e to the minus phi squared, where phi is some field, but it's a state. So, if I make some of, all these are words which we should be careful about. It never happens that something can happen spontaneously in the bulk, without, unless you violate something very basic about physics.
Excuse me. So what about Lieb-Robinson bounds, which restricts, propagation?
They are always looking at, but you see, they're always looking at factorized Hilbert spaces. There's something which is much deeper here that's going on. These bounds are always saying if you have two commuting sets of observables, you have a qubit here and a qubit here, then, but what's happening here is that you don't have independent degrees of freedom in the bulk and the boundary. So there's a redundancy in description between the degrees of freedom in the bulk and the boundary. As I said, when you want to think of questions of causality, the simplest case to think of is just the total energy. There are two ways we can measure, the energy of what's happening in the bulk. One of them is you just make a measurement by going to the bulk and measuring the stress tensor. The other is you measure in a theory of gravity the energy by making a measurement of the metric on the boundaries of the room. We can't do that today, but that doesn't violate any causality, nor does it violate any bound, because there is actually a constraint that relates this bulk measurement to that measurement at infinity. So they are the same operator. You're not measuring different operators, you're measuring the same operator. It's an operator level constraint. Okay, so what are the cases in which... Yes.
You should go on, but I'm sorry I asked that question about grandfather earlier in a provocative, but to ask it more, I was trying to bring out that you're proposing something really quite remarkable, but now to ask it more seriously, what you're saying is, take a sphere, in a laboratory of big enough size, etc. There is an experiment you can do to determine the inner matter inside it by just being on the surface. Which will tell you, because of gravitational effects, what is inside, which you could not have been able to tell otherwise, right? And later you say, but as you have emphasized, this is an experiment which will be sensitive to G Newton and H bar. And there is no experiment done to date which measures a quantum effect in gravity, right? So if there is an experiment like that, and it's doable, we should do it in India. We should
we should do it,
What are the numbers? I know.
I agree. We discuss this. We discuss this, and I agree. I mean, my feeling is the numbers might be far from where we can reach, but we should definitely work out the numbers. You're absolutely right. In this 2-point function I wrote, I had the bad habit of actually suppressing all h and c. But if I had restored factors of h bar, I would have got a gh bar by c cube. Okay. So even this simple measurement is everything we get here is proportional to gh bar by c cube. So it's a quantum gravity effect, but it's worth definitely. I agree with you completely. We should work out the numbers. Yes, it's not been done, but this is the reason. One reason I find this interesting is that this is the kind of experiment which, in principle, you could propose as a tabletop experiment for quantum gravity. When we think of quantum gravity experiments, we often think of black holes and things which are very exotic. But this is a very essential, basic feature of quantum gravity. It's the fact that gravity is holographic. And it is in some sense a tabletop experiment. It's not a tabletop experiment we can do today, but it's a tabletop experiment that says you measure some gravitational flux and you measure the fluctuations of that flux and you measure how those fluctuations are correlated with other fluctuations. So it's not, many orders of magnitudes, or maybe it is many orders of magnitude, but it's not unthinkable to to think of how you would do this tabletop experiment, I think. That's one reason why I think these effects are interesting. They're telling us something fundamental about gravity in a familiar setting. Yes?
Yeah, but the question is, what is the magnitude of those fluctuations
Yeah.
in tabletop experiment?
It's G.
Compared to the magnetic, as compared to, the gravitational potential itself.
Yeah, I agree with you. It's the same question that Sandeep asked. So I don't have...
Is there any estimate, order of magnitude?
I don't have an estimate right now. Okay, it's a very interesting question, and it's something that can be worked out. You have to basically, let me not try and make it live on stage. We should discuss afterwards. Yeah. Okay. Okay, good. So let me say a few cases where these effects are not relevant. So I've been trying to tell you how these effects are very interesting. I now want to tell you two more things. One case where these effects are not always important. And in fact, it's important that they are not always important because, we don't live in a world that's obviously holographic to us. Okay? So there are several cases where these effects are not important. Please keep that in mind so it's not confusing. One of them is in fact the case of the young person who's living in some part of the world. If they're living in some part of the world and they don't have access to the rest of the world, so they don't have access to a Gaussian sphere, then in fact they cannot determine what's happening in the other part of the world. So this is a famous example that we use often in ADS CFT. It's called the Ryu-Takenagi formula, where you take a spatial slice and you divide into two regions. So this is the region R and this is the region R bar. And in this case, there is no measurement you can make in R that tells you what's happening in R bar and vice versa. Okay? The kinds of geometric configurations I was talking about were always geometric configurations where you had a Gaussian surface where one region R surrounded R bar or vice versa. Okay? If you are in this kind of a setup where you have access to observations in one half of the space, you cannot determine what's happening in the other half. The second kind of setup, and this is actually also important, is that even if we had access to the walls of this room, we don't have detectors that determine instantly what's happening in the middle, and that's because in principle these effects are hard. In the examples I was giving, they were perturbatively hard, but in fact by introducing a suitable background you can make them non-perturbatively hard. Okay? So if you want to think of two different states, and the kinds of states you have in the bulk, there are e to the possible s states you can have in the bulk, not the simple two-particle example I gave in the beginning, two-point function example I gave, then it might require very high precision to determine what's happening in the bulk. Okay? And if you post-grain observations sufficiently, and by introducing a suitable observer, which I don't have time to explain, you can go back precisely to the kind of picture we have of local quantum physics. This is a feature, it's not a bug. It's a feature because it tells us that local quantum field theory that we use every day is actually a very good approximation. There's a reason why people don't have to all the time worry about the fact that gravity is holographic, even though we think that in our world gravity exists and gravity is quantum mechanical and it's quantized. We don't often have to worry about these quantum mechanical or holographic effects in our world, and the reason is that for many practical cases they are not important. One analogy I sometimes like to give is that you should think of these holographic properties of gravity like unitarity. Physics in the end is unitary. So if I give you the initial state, then I know the final state in principle. Okay? However, in reality physics is dissipative. Our everyday experience is that physics is completely dissipative, right? If I roll this thing, it comes and it stops and I can't actually tell you the initial state. And that's because I've suitably coarse-grained my observations and I've thrown away some information, and by doing that I recover the fact that physics is dissipative. In the same way, in the case of gravity, if you coarse-grain the set of observations you're making and you throw away some information, then you end up with a picture which corresponds to a usual local picture of physics that you have. Okay, and that's a feature and not a bug. I have 5 minutes left. Okay, let me take 5 minutes more. Be a kind chair, and let me try and explain now some consequences for black holes. I'm running way over time, but let me try and explain how this is important for black holes. I'll try and go through this fast because this part is not technical. Okay, so Sandeep in the morning talked about the black hole information paradox, which is a paradox that has been important in understanding quantum gravity. And the paradox is, very quickly stated as follows. Think of a black hole that forms. As I said, on these cases, time goes along the y-axis, and this brown stuff is some matter that's going and falling. You have some matter that collapses in on itself, and that forms a black hole. And when you form a black hole, you get what's called a horizon of the black hole. This purple line is what's called a horizon of the black hole. It's the region where once you cross, you cannot escape back to infinity. Okay, that's how you define the horizon of a black hole. Now black holes we call black because classically, their area always increases. You can sometimes do something to decrease the mass of a black hole, but classically you cannot do anything to decrease the area of a black hole. However, Hawking found that when you add quantum effects, something unusual happens, and that is that you can have these vacuum fluctuations near the black hole horizon, and when you have these vacuum fluctuations near the black hole horizon, it might happen that from these vacuum fluctuations you get some pair creation, and one of these, these particles in the pair goes off to infinity while the other particle falls into the black hole. And if you work this effect out carefully, then you find that if you have an observer at infinity, they will see a steady stream of radiation emerging from the black hole, and Sandeep gave the formula for the temperature, which in fact only depends on some macroscopic properties of the black hole. That's also what leads to this understanding of the black hole entropy as being 1/4 of the area. Okay. Here we are more interested in the fact that the black hole has a temperature, and what the temperature tells you is that just by conservation of energy, if the black hole is radiating some energy, then eventually the black hole will evaporate and cease to exist. But Hawking argued famously that because this radiation seems to depend only on the mass of the black hole and the charge and the angular momentum and a few coarse-grained properties, you could have a situation where you took two stars, maybe one had more hydrogen, the other had more helium, or they had some other difference in configuration but they had the same mass. They both collapse to form two distinct black holes, but then these black holes evaporate to give you radiation, but the radiation is the same because the mass of the two black holes was the same. Okay? And therefore, it might seem that this radiation is uncorrelated with the fine-grained details of the initial state beyond some coarse-grained details like the mass and the charge and the angular momentum. Okay? And therefore, it might seem that time evolution arrows cannot be reversed. Okay? Now you see that this is a problem, and that's why the title of this talk had reversibility of time evolution. It's a problem because in physics we imagine that we can always reverse the evolution of time, at least in principle. Maybe in practice we can't, but in principle, one initial state should give you one final state, and this kind of process where you have two different states that lead to the same final state is a disaster, and it would be a problem for combining gravity and quantum mechanics. There's a more formal way to say this, which is by measuring the von Neumann entropy of a region of this future boundary Scri+ that I talked about, and Hawking's argument imply that if you just look at this von Neumann entropy just keeps increasing as a function of time, because you have this radiation that's coming out and this radiation is in a mixed state, and because this radiation is in a mixed state, this von Neumann entropy keeps increasing, and therefore at the end you have some finite von Neumann entropy that corresponds to the entropy of the radiation. Now while we are familiar with the second law of thermodynamics that tells us that the thermodynamic entropy should increase, we don't want the von Neumann entropy to increase. The von Neumann entropy of a state always remains constant. If you start with a pure state, it's 0, and quantum mechanics tells you it should always be 0, and therefore this kind of curve is basically restating the paradox that I stated before and telling you there seems to be some problem in combining gravity and quantum mechanics. Okay. However, if you now go back to the pictures I've been telling you about, you see what this picture of holography tells you is that in fact information about what's happening inside the black hole is always available outside. Okay? So it's not true that information is lost if in this process of black hole formation and evaporation, and that's because if you think about it carefully and in a suitably fine-grained manner, then this information is always available to the outside observer. And the idea that we had that there was some information that went inside that was lost to the outside observer is false when you think carefully about effects of quantum gravity. Okay? So in particular, there's a more formal way to state this, which is that if you go back to this entanglement entropy or this entropy on part of Scri+, one can prove that in fact this entropy, if you believe this using the same arguments that I gave at the beginning of this talk, this entropy doesn't change as a function of time, it just stays constant, which is what you would expect of a von Neumann entropy, that it should not change with the physical process in the bulk. So using exactly the same arguments we gave, you can show that if you look at an entropy of a segment of Scri+, this entropy just stays constant. Okay. Now of course this is different from Hawking's suggestion, and therefore, and this has been one important thing which one would like to understand, one would like to ask, where is it that we think there's an error in Hawking's argument? This is an important question because you see everyone agrees for a long time that Hawking's argument was somehow incorrect, and we believe that quantum mechanics should hold and there should be an error in Hawking's argument. But the question is, where in Hawking's argument is there a mistake? So in fact, there are 2 points you can make about Hawking's argument. One of them, which is perhaps already familiar to many people who do statistical mechanics, is that you shouldn't say that, well, you had radiation and the radiation only depended on the temperature, and therefore it looks like information about the initial state was lost, because this is something that often happens in the process of thermalization even of ordinary systems. It often looks that if you don't keep track of very fine-grained observables, you tend to lose information. I already alluded to the example of dissipation some time back. So that's the first point. It is that if you want to differentiate between pure states and mixed states, you have to keep track of effects that are exponentially suppressed in the entropy of the system. This is just a result from quantum statistical mechanics, doesn't have anything to do with gravity, but it tells you that the argument where you just say, look, the black hole radiation depended on the temperature and not on other effects, is a little sloppy. You have to be much more careful. In fact, Hawking was more careful, but Hawking's more careful argument was based on locality and factorization. And if you want to ask where is the real error in Hawking's argument, it's there. So if you open Hawking's paper, you will see that Hawking says, the font is a little small, but what he imagines is that you look at the space-time of the black hole, and he imagines that you can factorize the space-time into 2 parts. You can factorize a set of observables into one part that corresponds to what's called the hidden surface, which is maybe hard to read here, and one part that corresponds to the part which is outside the hidden surface. So there's a set of observables inside the black hole and a set of observables outside, and you can factorize all the set of observables into those 2 parts. And then he said the observer outside has a principle of ignorance about the inside, which is that the observer outside doesn't know anything about what's happening inside, and therefore they lose information because the inside is lost to them as the black hole evaporates. Okay. However, the error that Hawking was making was that he was not keeping track of these effects of quantum gravity that tell you that in fact the observer outside doesn't have a principle of ignorance, but rather has a principle of information and can determine everything that's happening inside. Okay. So if one were to ask where was the error in Hawking's argument, one would say, well, here is the error in Hawking's argument in this particular part where Hawking assumes that there's a principle of ignorance and that the outside observer is blind to everything that's happening inside except for the mass, charge and angular momentum. That's a classical picture and it's an intuitive picture, but it's not true in quantum gravity. Okay. Once more, this is what I already said at the beginning. When you say that information is available at the horizon or outside the horizon, it's important that we are not saying the information jumps from what's happening here to here, but rather that the process of Hawking radiation which is happening here is already in causal contact with the matter that fell in. So it's rather that you cannot erase traces of information from outside. It's something we already discussed some time back. And so it's not that we are postulating there's some non-local dynamics, so there's something exotic or non-local that's causing information to jump from inside to outside. It's simply the fact that quantum gravity has this memory or has this unusual localization of information, and that's what causes the outside to be sensitive to all the details of what came inside, because you see the outside was in causal contact with whatever fell inside the black hole. Okay, maybe I'll skip the discussion of the Page curve. Let me just say one thing, and then I'll say something about recent developments. Many of you have probably also seen discussion of the Page curve, which is that Page, who was one of Hawking's students, famously argued that Hawking's answer was wrong. Page argued that Hawking's answer saying that the entropy was going up was wrong, but rather he said that the entropy of the region outside should follow a Page curve, in that it should first go up, as Hawking said, but then it should start going down. So this is consistent with unitarity because in the end the entropy is 0, and the Page result is actually an important result in quantum information. It's a completely correct result for cases where you don't have gravity and you can factorize a system into 2 subsystems. Those systems do obey a Page curve. It's an interesting and simple to derive result. However, the result we are saying for the entropy of the region outside is different from the Page result because it doesn't suggest the entropy goes up and comes down. It suggests the information is always outside. And the fact is that if you go and look carefully at what Page did when Page applied this result, Page derived this result, Page also explicitly assumed that the degrees of freedom divide into a degrees of freedom inside the black hole and the degrees of freedom outside. In a non-gravitational system, that would have been a correct assumption to make, but it was the same assumption of locality and factorization that Hawking also used. So although Page said, well, I think unitarity is correct, he was relying on the same assumption of locality of information in gravity, which is not true. So it's in fact the same error, we would say, that Hawking made in deriving the Page curve. Okay. Let me say one last thing about some recent computations, and then I'll stop. You see, there has been a lot of recent computations about the Page curve that many of you might have heard of, and especially those of you in the field certainly know about. And the way those computations are done is as follows. You think of a black hole in anti-de Sitter space, but then at the boundary of anti-de Sitter space, you add an additional non-gravitational path. So it's a model of a universe where you have a black hole, you have a gravitational region, which is this region, and then there is no gravity in this pink region. Okay? In such a setup, you can then divide this non-gravitational region into two parts and you can derive a Page curve. Okay? These computations of the Page curve don't contradict anything I said because they eventually Page curves in a non-gravitational system, and in this setup gravity is not dynamical throughout space. So it's a different universe from the kind of universe that we have. However, one thing you could say is even then, even though this is a different setup, and in these setups you can get a Page curve if you want, this picture I gave you of saying that information is always available at the boundary is useful even in these setups where you try to derive a Page curve. And one way it's useful is that you could think of the following setup. You could think of preparing a black hole in the theory of gravity, and then after that add to it a non-gravitational path. If you did that and you took seriously the fact that information in the gravitational region was already available at the boundary, then what this would tell you is that information in the gravitational region, by being available here, would then flow into the bath. So it would tell you in fact how in these models, which have been studied a lot in the recent literature, where you have a theory of gravity that's coupled to a bath, information about the black hole enters the bath. And the way it enters is that it's already present at the boundary of the gravitational region, and then it just has to flow locally into the bath. Okay? So in fact, there's been criticism of these models, not by us, but by Martinek and by Samir Mathur and others, who say, look, these models are wrong, they're giving the wrong answer because they're suggesting that information jumps from the black hole into this bath. But in fact, that's not the case. If you take seriously these holographic properties of gravity, you'll see that information is present already at the boundary and then just goes locally into the bath. Okay, let me stop here. I'll just summarize. The main point of this talk was that if you look at theories of gravity, they localize quantum information very differently from local quantum field theories. It's a simple effect. It's one that you can derive just by making some rather weak assumptions about the theory, but it's not a formal, some gobbledygook about formal properties of gravity. It's something you can really verify in perturbation theory, and that's the reason, at least personally, I find it so interesting, because I think it's something that's, it's true about gravity as we might be able to test at some point in not the very distant future. And these kinds of arguments shed light on why gravitational theories are holographic. Of course, as I said at the beginning, we learned that gravitational theories are holographic from string theory. It's string theory that first told us and gave us precise examples of holography, but now we can try and abstract away from those examples and try and argue that in any UV complete theory of quantum gravity, this property of holography should hold. And as I said, this is important for understanding the reversibility of time in quantum gravity, because if you don't account for these effects, you end up with paradoxes. If you do account for these effects, it gives you a resolution of these paradoxes, and these effects are also useful for understanding these recent computations of the Page curve. Thank you for your attention. Sorry for going over time. I'll stop here.
Okay, thank you.
Subrat, when you are telling factorizability, you mean quantum mechanics?
Yes.
And when you are referring locality, you are meaning gravitation. Am I correct?
No.
Because quantum mechanics, there is locality, sometimes it is referred to Bell's locality condition.
No, I was not referring to that. No. So maybe I should have been more clear. I was thinking, I was trying to make a difference between quantum field theory and quantum gravity. In quantum field theory, you have a set of observables. The set of observables are labeled by a position, by a point in space-time. Okay? So you can divide the set of all observables. So let's say you restrict yourself to one instant of time. Then the observables you have are just the field values at different points in space. You can think of a lattice. You have different qubits at different points in space. You can divide the set of all observables you have into field values outside some bounded region, and field values inside some bounded region. You take the product of them, that gives you the set of all observables in the theory. That's how things work in quantum field theory. In quantum gravity, I was saying that factorization doesn't happen, that the set of observables inside a bounded region are not independent of the set of observables outside, because there are constraints that tell you that they are redundant with some set of observables outside. In gauge theories you do, because so the precise thing I should have said was that there is a split property. Okay, the split property is a statement that you can prepare the state inside a bounded region independently of the state outside, provided you give me a small buffer region. Okay. So for instance, you might have said, let's say I want to put a lot of charge in this region. The observer outside can at least measure the charge. But if you give me a small infinitesimal buffer region, I can put a lot of negative charge, so the observer outside cannot determine anything of what's happening inside. So the split property is a statement that you can prepare a state inside this room and outside the room, give me the wall as a buffer, in such a way that the observables outside are completely independent from the observables inside, they are not even entangled. That's true in non-gravitational gauge theories, but not true in gravity.
I don't know whether that's the same as us saying that the algebra of observables factorizes.
Yeah. Factorizes is a bad word because sometimes.
So I was speaking in the sense of type 3.
Yeah.
I didn't want to use that phrase.
Yeah.
But typically, unless you're in quantum field theory and you have all space-time available.
Yeah.
It's not.
I mean, Sandeep and so on have analyzed a lot what happens in gauge theories, how you have to add these boundary degrees of freedom. But I want to make a slightly more physical statement, which is not, you see in quantum field theory also people say, forget about gauge theories. The Hilbert's, if you go read Walt's book, they'll tell you, Walt will say the Hilbert space doesn't factorize because of UV effects. I'm making a more physical statement, which is, you give me the state inside a bounded region, give me a small buffer, which will get rid of all my UV effects, and can I prepare the state outside the bounded region in a way that's completely insensitive to what's happening inside the bounded region? Answer in a theory without gravity is yes. Answer in a theory with gravity is no. That's a a theory with without gravity, even if it's a gauge theory, answer is still yes.
I think you answered a slightly different question, but perhaps
that's because I'm not interested in the very fine details of how you classify von Neumann algebras and what you have to add.
I think then the statement is true that you answered a slightly different question.
But it's a separate question from the message of this talk, which is a physical statement about is information inside available outside or not.
But fact of the matter is that algebra of observables, especially in gauge theories, does not factorize.
No, even the Hilbert space in a continuum theory doesn't factorize because there are boundary constraints, but but that's a mathematical statement that doesn't have to do with the fact that the information inside this region is not available outside. And the split property, if I had to frame it more precisely, which maybe I had in the slides, the split property is a statement that you give me a small buffer region and I can prepare the state inside and outside independently. The split property as stated that way is true exactly in gauge theories and in non-gravitational theories with or without gauge fields, and it's not true in the theory of gravity. So the precise statement is the split property fails in a theory of gravity. I'm using factorization slightly loosely. I could say split property, but it would just make less sense. Yeah.
So there's,
sorry.
There's one thing, and you can tell me later, which I'm not sufficiently clear about.
Yeah.
Can a set of observers who are, say, at infinity or very far away, do a coordinated set of operations and instantly affect something deep inside?
It seems the answer is yes. So if they do something, it's harder than measuring something. But I think the answer is yes. It's an interesting question. We can ask it in several different ways. For instance, you could ask, what if there's an observer inside to see that something was affected? Then the people outside would have to do something that would affect not just what you wanted to affect, but also the state of the observer. So it would make the effect much harder. This, by the way, is a question that one can ask independently of everything I said. It's an effect in ADS-CFT. You could ask, can you act with a boundary operator that changes the whole bulk? Of course, the answer in principle is yes. Then you can ask, how does someone in the bulk perceive it? And that's actually an interesting question, which I can try and describe to you in some more detail. But the answer in principle is clearly yes, and it's also true in ADS-CFT. I can act with the boundary in some way so as to change the bulk in a coordinated way everywhere. Then we can ask how hard is it and how does the bulk perceive it and so on.
So, but in asymptotically flat space also
I think
say you can do this.
I think so, yes.
Isn't that a bit shocking?
It's a bit surprising, but as I said, it's something we should have expected from holography.
Okay, thank you.
So I mean, if I
Yes, sorry, just one thing I wanted to add. You know, it's a bit shocking, except if there's a person inside, it's an extraordinarily hard measurement thing to do. So, you know, you have to kind of, it would be shocking if it was easy to do, but it's very hard to do. Yeah, okay, but we can talk more about it. Sorry, please, yeah.
So the split property, if I paraphrase it as saying that gravity cannot be shielded.
Yeah.
That's just basically what it means, right?
This split property.
All other interactions can be shielded with something, but not gravity.
Yes, since there's a blackboard here, the split property is a statement. I can prepare a state phi. You can see, and I have some observables inside a region, and some observables outside a region. So x is let me not call this state psi. Let me call this state psi. Yeah, and x are inside a region, and y are outside the region. Then I can always find a state psi so that this looks like psi 1 for the states inside the region and psi 2 for some other state psi 2 for the observables outside the region. So notice there is no entanglement. I have in fact made the correlator factorize. And the split property is you give me any state psi 1 and psi 2, I can find a different state psi that interpolates between psi 2 outside and psi 1 here, provided I have a small buffer region epsilon. And that's true, you know, in any case, in any non-gravitational theory. It's not true in gravity, because indeed, as you said, you can't use the buffer to shield what's happening inside from outside.
And one other small comment. Your flow of arguments seem to imply that if I assume holography, then all the good things follow.
No.
In the one second. In the sense that information problem at least is not there. If I assume holography. Now my question is, can I ab initio formulate holography as an abstract postulate in some very well precise thing, and then derive all these results?
Yes, but you see, the flow of arguments was not if you assume holography. The flow of arguments was you assume some basic properties of quantum mechanics and gravity, such as the Gauss law and the uncertainty principle, and holography follows from that. So it was very important I never assumed holography. The first part I tried to explain was, when I gave those arguments, was you just assume some simple statements about quantum mechanics and gravity, and any theory of quantum gravity forces holography upon you. So it's very
that's
important.
That's the part I am not clear. So,
so the arguments I was giving at the beginning were trying to say that holography is forced on you by quantum mechanics and gravity. You don't have to assume it. So,
as I said, I will have to think about it, because I have to understand precisely what is meant by holography and so on and so forth.
It is the statement that the operator algebra at infinity is complete. There are no operators in the bulk that commute with operators at infinity, and observations at infinity are complete. Observations in the complement of a bounded region are complete. That's the statement.
Actually, you talked about this computation of the page curves.
Yes.
So what are the methods? I mean, Monte Carlo on the lattice or something like that?
What is the what?
What are the methods of computing these page curves? Monte Carlo, or Monte Carlo on the lattice or something like that?
The page curves I showed at the end?
Yeah.
The page curves I showed at the end were page curves where page curves are interesting in many setups. Okay, you might be interested in non-gravitational setups. The page curves I was talking about was where you have a theory of gravity that's coupled to a non-gravitational bath, and there the way of computing the page curve is by a generalization of this Ryu-Takenagi formula that I just showed. There's a bulk, so you know conceptually the computation you're doing is a non-gravitational computation.
Okay.
You have a non-gravitational theory, you want to compute the page curve one part with the other part. Because there's a bulk dual, there is a bulk computation you can do which involves computing some minimal surfaces, sometimes doing something more sophisticated, which allows you to compute the entanglement entropy of one part of the boundary with the other part of the boundary. So it's one of the successes of holography or string theory is it gives you these formulas to compute boundary entanglement using some bulk gravitational computation. It gives you a dual way to compute that quantity. That's how those page curves are computed. What I was trying to emphasize was conceptually they are non-gravitational page curves. They are not the curve that Page originally had in mind. Page had a curve in mind where he was thinking you compute the entropy of the inside of the black hole with the outside. That's not what is done. What is done is you compute the entropy of one part of the bath with the other part of the bath. You use some gravitational computation to do it, but it's a non-gravitational computation. But the methods are that you compute some minimal surface, and sometimes they're more sophisticated, but the essential method is that of computing a minimal surface.
Is that non-perturbative?
It is, I mean, the entropy you might say is a non-perturbative quantity, but you compute the entropy to leading order and perturbation. The entropy itself might have an expansion, and you compute the entropy to leading order.
Okay, thanks.
So I just want to make a prediction, so you will prove me wrong.
Yes.
That to do your experiment will require if you have 1 GeV worth of energy inside
Yes.
and you're trying to tell if it's
Yes.
baryons or antibaryons
Yes.
or whatever, will require us to measure fluctuations on the scale of 1 part in 10 to the 38. And I hope I'm wrong, but that's what I come to by taking G Newton H bar and M squared
Okay,
dimensionally. Now, I hope I'm wrong, but
I can't do that. You have the advantage of having done the calculation, which I haven't. But it is whatever you get by looking at G Newton times G H bar by C squared is C cubed is the coupling constant.
Yeah.
It is what you get. But it's, you see, it's the weakest quantum gravity effect you can get. If you can't measure this, then it's very unlikely. I mean, maybe in cosmology you would measure something. That's one place. But if you want to see some quantum effect about black holes, that would be exponentially harder than this.
Yeah, no, I agree.
Yeah.
I only say this so you
Maybe.
prove me wrong, but we should do it
Maybe
more
one part is-
carefully.
yeah, maybe.
We should do it more carefully.
Okay, we should
And
do
if
it
it's
more
1 part in 10 to the 38, we go home. Yeah, I think
It's-
even Vivek can't do that, but we
Yeah.
should be sure.
Okay,
You know,
maybe.
That's
Yeah,
just to say.
yeah.
Okay, I will ask the last
Yes,
question.
okay.
So correct me if I'm wrong.
Yes.
So I think in your argument it's necessary that the Hamiltonian of the bulk theory should be available in the
Yes,
boundary
yes,
theory,
yes,
right?
yes.
So that's like a thing that for quantum gravity or in
Yes.
string theory, if somebody can show that there is some part of the Hamiltonian that is coming from say some bulk region,
Yeah.
then the entire argument will be.
Yeah, so that you mean the Hamiltonian is not a boundary term.
Yeah,
You
let's
know,
say
the reason the
quantum
Hamiltonian is a boundary term is basically because of diffeomorphism invariance in gravity. It's the fact that because you have diffeomorphism invariance, the Hamiltonian forces you to, is forced to be a boundary. It's a very robust property of gravity. I think it's true in string field theory, for instance, that the Hamiltonian, so I don't think the fact that the ABM Hamiltonian doesn't exist, but it's true. I'll give you an example of a theory of gravity where it's not true. In massive gravity, if you look at these massive theories of gravity, in fact in these page curve computations, many times when you use these W holographic models, the theories of gravity are massive. And then it is not the case that the Hamiltonian is a boundary term. The gravitational theory is Higgsed. And in this Higgs theory, you don't have a term you can measure, and then these arguments don't work.
In string field theory, no one has shown that.
You're right, no one has shown that. Ashok tried to explain to me why it was clear, but you're right. We can talk more about it.
Okay,
Yeah.
thank you. Okay, let's thank Subrat for this nice talk. We will reconvene at 3:50.